We were discussing one differential equation. Now, in this section, let's have a look at a system of two or more differential equations. Let's start with a system of two equations for two unknown functions. So, we want to find two functions. X is a function of t and y is a function of t that satisfy some differential equations. The derivative of x with respect to time t is sometimes denoted x prime and sometimes, especially in physics, denoted by x dot. Dot is often the symbol for the derivative with respect to time. And similarly, the derivative of y with respect to t is sometimes denoted by y prime and sometimes by y dot. This prime is derivative with respect to time t, not with respect to x. X is now, together with y, the dependent variable, and the independent variable, the argument, is t. So such a system of two differential equations may be in the form, say, f1 of x, y, and t, and y derivative is some function f2 of x, y, and t. An example might be x derivative is equal to x minus y times t, and perhaps y derivative is e to x plus y times cosine of t squared. Just two functions, two expressions that may in general contain x, y, and t. If the right-hand sides do not contain t, then such a system is called autonomous. If x dot is f of x and y alone, and similarly y dot, f1, f2, if x and y alone. If there is t in the right hand side, we call the system non-autonomous. Further, if x and y are only multiplied by some coefficient and added, and no more operation like exponential or nothing more complicated, we call such a system linear. And if there is some other function, we call it nonlinear. Let's start with a system of two linear autonomous differential equations. In general, they may be in the form x dot is a11x plus a12y, and y dot is a21x plus a22y. Then we can arrange these numbers into a matrix, and we can call it a11, a12, a21, a22, and we can call the vector xy as z with arrow. And then such a system can be described with the differential equation z arrow, meaning vector, dot, meaning the time derivative, is equal to the matrix A times Z. And we will discuss this system in more detail now. In a special situation, if a12 is 0 and if a21 is 0, then this system of two equations actually splits or decomposes into two independent equations. We can easily solve this one using separation. If we write the derivative as the ratio differential, we see that x is 0 is indeed a constant solution, and for non-zero x we can use separation. We can integrate and we arrive at logarithm absolute value of x is a11t plus c. And then if we remove the absolute value and if we remove the logarithm, we can find that x at t is exponential of a11t times some constant which has the meaning of the initial condition x0. And similarly for y, we arrive at the solution y at t is exponential of a22 t times y at 0. Well, and now in the general case, when these a12 and a21 are not 0, the two variables are related, and if we remember the eigenvalues and eigenvectors of a matrix, namely, if we have a vector v such that its image under this multiplication is parallel to the vector itself, that means AB is equal to some number times v, and we call this number lambda. We denote this number lambda and we call it eigenvalue and the corresponding eigenvector. And this is a very useful concept because if the initial condition z0 is on the line given by the eigenvector, then the velocity is the matrix times the eigenvector, which is in the same direction. So if we are in the xy plane, and the vector z0 is somewhere here, which is on the line given by the eigenvector, then the velocity is in the line as well, either this way or this way. That means we don't leave this line. Actually, this allows us to reduce the two-dimensional system into a one-dimensional problem. Because if z0 is some number times the eigenvector, then so is the derivative z dot. And then we are in the line forever, and we can assume that z at t is given by some coefficient alpha at t, which may vary in time, times the eigenvector. And if we substitute this form into the differential equation, then on the left we have the time derivative, which is alpha derivative, and v is a constant. And on the right we have a times z. A times, but z is alpha v. Alpha is a function of time. But this is a scalar, which depends on time, but this is a scalar, and we can write a scalar in front of that, and we have alpha AB. But v is the eigenvector, so AB is lambda v. And we have the equation that lambda derivative times v is alpha lambda v. So this vector multiplied by a number is equal to the same vector multiplied by this number. And if v is the eigenvector, we assume it is non-zero. So this number, alpha derivative, must be equal to lambda times alpha. Lambda is a constant. This is the eigenvalue of the matrix. And alpha is some unknown function of time. But this is a similar equation like the previous one, and we can use separation, and we arrive at the solution alpha at t being e to lambda t times alpha at 0. And when we have the time dependence of lambda, we can write it here, and we have the solution. Z arrow t is equal to alpha, which is e to lambda t, times alpha at 0 times v, which is the initial condition z at 0. And for a 2 by 2 matrix, if we find two linearly independent eigenvectors, then this is true for lambda 1, z0, and z0 was some number times the eigenvector, so we can write it as some multiple of the eigenvector. And if we have two eigenvectors and two eigenvalues, then we can call the first one lambda 1 and v1, and we can multiply by a constant c1, or we can consider e to lambda 2t times v2. This is the second eigenvector with the corresponding eigenvalue. And because the system is linear, then if this is a solution, then the linear combination of these two solutions is again a solution, and it is the general solution of this system of differential equations. So the computation goes this way. We look at the system of equations, we write the matrix, we find the eigenvalues and eigenvectors, and then we build this general solution. Let me illustrate this in the following example.